Okay, so we go back to see this exercise. So as I mentioned, the water can be to be the bubble. So we have some requirement conditions. The first requirement is the inner pressure should be higher than ambient pressure first. And the second is depend on how large of your bubble. So the different diameter, you will have the different pressure conditions inside the bubble. Okay, so we go back to see these questions exercise. So we actually know the diameter D in our problems is the 2 millimeter. Okay, so it's equal to the 0.002 meter. Okay, and then because this is the water, so we actually know the surface tension for the water around the 0.073 Newton per meter. Okay, so you need to keep in mind you have some image for the surface tension of the water, the number showing here. Okay, so as the false diagram showing here, you know you have the FP. FP is the inner pressures. FP is the inner pressures. So we need the maybe we call that the inside pressures. Okay. And we need to convert the inside pressure to the force, right? So this is just the inside pressure is PI, but we need to convert the pressure into the force, pressure force. So the pressure, inner pressure should be multiplied by the acting areas, and we can convert the pressure to the pressure force. So the PI multiplied A is equal to FP. So we should compute the pressure force first. So this is our first purpose. And the second, the force comes from the surface tensions. Okay, so we call that is a surface tension force. And then in here we use the F sigma. So we also know we need to use the surface tension sigma multiply the length of the interface between the two material. Right now the material interface is the air and the water. Okay, so we first compute the FP. And the questions in here, we would like to know the PI, how large of the PI. PI is the inner pressures. Okay, so we have the FP and equal to the PI, and the area is working on here. Okay, and if we see the project view, the map view, the area is in here. So we need to compute the circle areas. Okay, since we already know the diameter is the D, so half diameter square pi is our acting area. It's our acting area. So we just reorganize the equation in the PI and the 4 over D square pi. So this is our FP. And this is for the first purpose. And the second, the surface tensions, F sigma. And we know the tau as the sigma is surface tension of the water. And how about the length? How about the length here? Okay, so the length, again, we consider the length is the circle length. The circle length. So the circle for the radius. So the circle radial length is equal to the d pi, right? So right now, we can have the force balance between the Fp and the F sigma. So we have the force balance Fp is equal to F sigma. So that's the Pi for d squared pi is equal to sigma d pi. And some parameter we can cancel out, such as the pi and the 1 times d. Okay, so we rearrange the equations. We know that the pi is equal to 4 sigma, 4 times sigma, and divided the d. Okay, and but the question is, we need to compute the number for the inside pressures. So we have the two informations is 0.002 meters, and the surface tension is 0.073. So we just put the number inside the formula. So it's 4 times 0.073 Newton per meters, divided the diameter is the 0.002 meters. So the meter unit can cancel out. So the another cancel out is not the same. So I correct the here is the meter and this is a meter. So the final unit is meters square over newtons is equal to the pressures unit. So you can use your calculator to compute the number. So the number is equal to the 146 Newton per meter square. And this the unit is equal to the par, right? So we just change the unit to the par. So here you can make the comparisons. As you remember, the environment pressures, always we call that the 1 atm, right? The 1 atm is equal to 101.3 kilopar. So that you compare the two numbers showing here, okay, showing here, they are uncomparable, right? The inside pressure showing here is quite smaller than the environment pressures. Okay, so that means we only need a little bit changes pressures compared to ambient pressure. We can have the bubble. And depending on how the bubble size you want. So if you look at the formula showing here, if you let to the smaller bubble, that means the diameter is small. And then the inside pressure will increase. Okay, so the idea is the smaller diameters, you need to increase the inside pressures. So in other words, if you would like to have the larger diameter of the bubble, you need to decrease the inside pressures. Okay, so maybe the exercise is quite simple, but in our class, we always focus on the final formulas. And we try to explain the physical phenomena by the formula. So you can compare each other just based on the formula. You can adjust the different. You try to reconsider if the D decrease and what's happened in PI. And you can understand better understand the physical phenomena for these problems. Okay, so this is I would like to emphasize. So we always look at the final formulas, and we try to use the final formula to explain the physical phenomena. Okay, this is a very good exercise, and the final exercise for the surface tension is the needle floatings. As I mentioned, the 轻功水上漂, right? So if we see the movie, we just put the stainless needles on the glass, and we put the water, and right now you see the needle is floating, right? But somebody just broken the force balance, and the needle will drop down. Okay, so that's the idea how the needle can floating. That's because we have the surface tension provide the force upward, and also overcome the weight of the needle. So the question is, if we go back to see the exercise, we actually know, again, we would like to apply the force balance to determine the size of the needle. So the water surface tension already fixed. So if you put the different size of the needle, maybe some needle will just drop down, right? Maybe some needle can floating. So how about the largest diameter you can support? So that's our problems. How about the largest diameter of the needle can be supported by the water surface tension force? Okay, so we just consider our needle in here. Okay, maybe this is our needle, and it's not correct, right? Because the needle one side is pin, not like cylinders. But we for our question, you can see we neglect the end effect. That means both sides we consider the cylinder shape, and some shape is pin, but we just neglect. Okay, so this is our needles and floating on the water. So the ambient is the waters, and this is the line. This is the two lines just close over the water surface. And for the end of the needle, we just neglect the end effect, so we don't consider the force located on the end of the needle. Okay, so we only focus on the cross line between the interface, along the interface between the water and the needle. So why I draw these two lines? Because I actually know the surface tension force will acting along the two lines. So we have the surface tension force acting on the two sides of the needle. The side is the other interface between the water surface and the needle, just the close over lines. Okay, and the sequence, we know that the first one, this is supported by the surface tension force, and we still have the weight of the needle, right? So we have the weight downward of the needle. So we need to know the properties, physical property of the needle, because the different property needle have a different specific weight. We have provided a different weight, right? So we see the questions already tell us the needle material is the stainless steel with the SG is 7.7. Okay, so that's our first. We need to compute the weight, and again we need to know the gamma steel. So I use the gamma S, multiply the volume, so we have the weight, right? But we didn't know the gamma S right now. So we can follow the SG definitions. We have the SG numbers. We know that the SG is equal to the gamma S divided the gamma W, right? The gamma W is relatively to the water. So the gamma S is relatively to the water specific weight. So we know that the gamma S is equal to the specific gravity multiplied the gamma W. Then we can put the formula, go back to the equations. So the weight is equal to the Sg multiplied the gamma W. As we know, the volumes in here is cylinders. So we can, we know that the 4 over d squared pi is the area multiplied the length. So we didn't know the needle length. So we assume the length in here, the length, okay, in here is L. We didn't know because the question didn't provide the whole length of the needle, okay? So we assume that the needle length is L. So we have multiplied the L. Okay, so this is the weight of the needle. And then the second, we need to compute the F sigma. So as we know, this is questions for the water. So we know that the water on the 20-degree conditions is equal to 0.0728. But here I just know we have the sigma and multiply the length, right? And so we multiply the L, but we have the two sides. We have the two sides of the needle. So here we need to twice times of the sigma L because we have the two sides cross interface. Okay, so go back to have the force balance. So we just put the F sigma is equal to the weight. Okay, so we know that the Sg gamma W 4d squared pi L 怎么一直有人一直耐呢？怎么朋友这么多？OK， 然后sorry， so the sigma L twice times, and we look for some parameter we can cancel out again. So first we cancel out the L, right? So that means this problem we don't need the L. No matter how length of the needle, because in here the formula we cancel out the L. So we don't need to know pi area knowledge is not for the length of the needle. And then only L can cancel out. So we just keep our answers. The purpose we need to know the D, right? So we just put the D squared on one side and move other parameter to the right hand side. So here is 8 times sigma divided the Sg gamma W and pi. Okay, so we put all of the number we know already. So here is 8 and the sigma is 0.0728 Newton per meter divided the Sg is the 7.7. The Sg there is dimensionless parameter, so there is no unit. And the gamma, we know the water gamma is 9810 Newton per meter cubic. And the pi is, I use the 3.14. Okay, so you can double check the dimensional is correct or not. So the Newton cancel out, and I cancel out 1 times meter. So the meter here to become the meter square. So you use your calculator to compute the answer. So the 8 multiplied 0.0728 divided 7.7 divided 9810 and divided the 3.14. Okay, so I just write down the numbers show my calculator is 2.4 maybe 6 and the 10 minus 6 powers. And right now the unit here is the meter square. So we need to compute the root of the d square. So the d is equal to root. So around the 1.57 10 minus 3 meters. And as you can see, the final answer, we use the millimeter dimension. So it is finally equal to 1.57 millimeters. Okay, so this is our final answers. But you see the balance. You see the balance formula as we use here. This is our final force balance formulas. So as you can see, if you have a larger surface tensions, and then you can support the larger needle. It's common sense, right? And if your needle is not the stainless steel, you change the material of the needle, that will be the SG will be changed also. So you will the supported largest diameter also be changed. Okay, so that's quite a simple idea for the surface tensions. Okay, so if we go back to see the physical phenomena I showing here, so how many properties will be observed in our exercise? So in our exercise, we finish the capillary rise and the bubble formations and the pressure inside. And we also practice the exercise related to the walking on the water phenomena. So only detergents and the first one weakening, we don't have the exercise. But the weakening is usually observed in our life, like the 排汗衫. Okay, so if the clothes have the two phases, the one phase can water hating, and the one phase can water loving. So the water loving, so just the 汗就可以从那边吸进来，然后再排出去嘛。So one phase water hating, so cannot keep the water on the clothes. So the water can go outside. But another phase just keep the water. So 排汗衫就是这种道理。So you can adjust the material properties in your clothes, and sometimes we call that the fiber coat activity. Okay, so let's two properties. The fiber pressures. Okay, also very common in our life. As the diagrams, we call that this is the phase diagrams. So you see the blue line is the interface between the liquid and the vapor. Okay, between the liquid and vapor. So some important words, numbers, you see. We have around the 100 kilopascals. And if you first to right hand side, you first to the right hand side, okay, and you can find the temperature is around the 100 degree. Okay, so as we know here, the number, the 100, we know that is around the 1 atm, right? Because the 1 atm is equal to 101.3 kilopar. Okay, so you see the unit here is kPa. Okay, so this is our environment, the 1 atms. We will have the one based on the phase diagrams. So you have the 100 temperatures, and we usually we call that is the boil temperature, right? The boil temperature. So sometimes we go hiking and the elevation changes to be the high. So the elevation changes to the high, so the environment pressure will decrease. So if the environment pressure decrease, so we will draw another line, maybe decrease to the 10 kilopars. And at the 10 kilopars, we based on the phase diagram line, maybe we only have for the 50 degree boil temperature. So that's a normal phenomena. If we go to hiking and the elevation change to high, we cannot cook the soup or meat because the boil temperature is not high enough. Okay, so that's a very common physical phenomena. Okay, so, but what the idea I would like to emphasize in this class, the vapor pressure is very famous in our fluid engineering problems. As you see right now, the example I change the condition, the water at the 20 degree flow through the nozzles and then the boils. It's plain white. Okay, it's plain white because we fix the environment nozzle like the run pipe, and the flow along the run pipe, and at some specific condition, the water flow start to boil. But the reason why, because the environment didn't change, but the water just flow, but we can observe some water boil to be the vapors. OK， 就是现在的环境不太一样，我们在同一个管子里，可是水却在流动的过程中竟然气化了，那怎么会这样子？刚才我们说的去爬山或什么，那是压力有变化嘛，所以条件会变嘛。可是如果我们在管子里面水在流动，怎么会产生气化？ So that's the problem, because why the liquid can be the vapors. That's we fix the condition here. We fix the 20 degree, right? Right now we fix the 20 degree conditions. So only one possible answers. The pressure should be decreased because we fix the 20 degree environment. And if the pressure decrease, start from high to low, and you will cross over the blue line. If your pressure under the blue line, that means the liquid will become the vapor. So that's the only one possible answer. The pressure should be decreased, even though you fix the 20 degree temperatures. And then the liquid can to be the vapors. Okay, so only, and how can we have the pressure decrease? So as the words are showing here, that's because the flow speed become larger, and then the pressure will be decreased. And this idea just we talked that the Bernoulli equations, but I didn't teach before, and the Bernoulli equation will teach in chapter 4. But right now I directly tell you the velocity increase and then the pressure will decrease. Okay, so we go, and then there are some very important the vapor pressure, you need to keep in mind because usually our problem always at the room conditions. The room condition, the temperature is around 20 degrees. So you need to keep in mind the vapor pressure at the room condition is 2.34 kilopascal. Okay, so you need to keep it in mind for these numbers. So the next slide, as you can see, what the pipe I talked to you, I call the nozzle. Nozzle 就是束缩管. So the diameter along the pipe will change. So as you can see, the different cross section will have a different diameter of the pipe. And in this pipe condition, we call it the nozzle. And you see, this is the distance, and this is the pressures. You can compare both figures. You know that when the diameters become smaller, and the pressure will decrease, right? If this is a normal diameters and the pressure are the normal, that means at this cross section area, the speed will to be the higher, and the speed to be the flow speed to be the higher, and then the pressure decrease. If the pressure decrease below the dash line showing here, and the dash line is, I say, 2.34 kilopascal. If the lower end and the liquid will become a vapor bubble, the liquid become a vapor bubble, the bubble will destroy the infrastructure. Like you can see, some infrastructure service will be broken. So the bubble is very dangerous and powerful. If we have some designer, they didn't control the flow speed. If the flow speed too high, and will have the lower pressure conditions. The lower pressure condition, if you lower than the vapor pressure, and then the liquid will become the bubble, and the bubble will broken some infrastructure. Okay, so for engineer, we are focusing on this problem in our case. So only one possible solution, when we design some pipe and a nozzle, and like we have a reservoir, so we can have some spillway. If we design a spillway, we need to control the flow velocity. Okay, so this is a very important problem for our fluid mechanism class. So that's why I emphasize here and take a time to explain more details. OK， 这个是很严重的问题，就是大家都想说，那水就让它流越快，不是越好吗？反正早点可以送过去，早点到，早点可以用，就了事了嘛。但是流速只要太快，就会产生低压的条件。产生低压的条件，如果低到我们刚从 phase diagram 那个 diagram 可以发现，只要低到蒸汽压的话，它就会气化。气化以后就会产生气泡，就会去撞击这些结构的表面。那是一个很严重的问题。我们想说，泡泡不就是很简单的东西，怎么会这么痛，对不对？但是它就是这么痛，它就是有这么痛。Okay, so the final properties. This is our final slide today, and this is a final property. We call that specific heat. Okay, so the specific heat, the physical definition, very clear. That's the heat we require to increase 1 degree for the material has the 1 kilograms. But so this is a specific heat, always focus on the problem for the gas, not for the liquid. And as we know, the gas, if we change the pressure or change the temperature, the volume will change also, right? And the physical property also change, like the density. So sometimes we try to calculate the specific heat. We will have two conditions. the one condition we will fix the constant volumes, and we measure the specific heat. And the second, we fix the pressure. So under the constant pressures, and we have another specific heat. So two specific heat, one we use the CV, another we use the CP. That depends on we measure the specific heat under different conditions. And why we do that, as I mentioned, because we are focused on the specific heat for the gas. But the gas will change some physical property depending on the temperature and the pressures. So you do the laboratory experiments to measure the specific heat. You need to fix the pressure or fix the volume, and you have the different answers of the specific heat. So just based on the specific heat, and we define the ratio between the CP and CV, and we call that the adiabatic exponent, and use the simple K. Use the simple K. So there are some examples, some important number like the air condition for the air. We know that the CV and the CP and the K is 1.4. So in the future, if you meet the problems for the gas, you need to consider the specific heat, especially for the thermal problem. You have some problem related to the thermal ideas, so you need to keep it in mind. So that's why the final sentence right down in here, I just highlight the specific heat for the air. Okay, so 好，大放送，好不好？那今天我们就卡户一下。